So in this video we're going to look at composition of functions. We'll look at three distinct things: writing a function as a composition of two separate functions, that's where we'll start, finding the domain of a composite, and also evaluating composite functions at some given value of x. So starting off, we are asked to find, let me talk about how this reads. So we have two different notations. We have f of g of x, or the composite of f and g of x. These mean the exact same thing, we just happen to have two notations for that. And so you'll see as we go through the video in the section that we're going to run into both of those notations, so you want to be comfortable seeing both of them. For this first example, we're asked to find f of g of x and g of f of x. So what does that mean? It actually kind of means what it looks like. I forgot to get my pen ready here. There we go. If you think of what f of 3 would look like relative to this function, that means we would be putting in a 3 everywhere there's an x. When we're saying we're finding f of g of x, we're going to put g of x everywhere there's an x. So like for this function, it means we're going to find f of 2x minus 5. That would be equivalent to saying find f of g of x. So we're going to evaluate f at g. So to do that, we'll go 2x minus 5 quantity squared minus 3, and then can't forget that x, 2x minus 5 again, and plus 2. I'm just going to get rid of the stuff over here. So this piece, remember, is you can use perfect trinomial square formula, the a squared minus 2ab b squared, which is what I'll do here in a second. Or if you're not comfortable with that, write it out side by side and FOIL. You're going to get to the exact same place. I'm going to use a squared minus 2ab plus b squared. And remember, if we have something in the form a minus b quantity squared, this is what it FOILs out to. So it would be 2x times 2x, that's our a squared, so that is 4x squared. 2 times a times b, so that's 2 times 5 would be 10, and then the 2 in the formula, so that would be 20x. So essentially you just multiply these two together because they're your a and your b. Remember, this is a minus b quantity squared. So these are your a and your b, so you multiply them together and double it, is what that says. And then minus 5 quantity squared would be plus 25. And then we'll distribute the 3 through, so that's going to be a minus 6x plus 15, careful with the sign there, and plus 2. And then we just have to collect our like terms, so it looks like the highest one we have 4x squared, got a minus 20 and a minus 6, so that's going to be minus 26x, and plus 25 plus 15 plus 2 would be 42. So that would be f of g of x. For g of f of x, that means we're going to evaluate g of x. So for this x right here, we're going to plug in f of x. So that one would look like, where'd it go? There we go. 2 times x squared minus 3x plus 2 minus 5. So there's this plugged in right there. And that one is g of f. Distribute the 2 and collect terms. So 2x squared minus 6x plus 4 minus 5. Plus 4 minus 5, so that'd be a minus 1. So that one is g evaluated at f of x, or the composite of g and f of x. You don't have to have two functions. You can evaluate a function at itself, if that's what the math calls for. So this one would be this inserted into the x's of itself. So f, notice we're using that other notation now, f composite f of x. Excuse me. So it'll be x squared minus 4x, and that is squared, so that's my new x right here, and then minus 4 times itself again, x squared minus 4x. So if you just think about if you're finding f of 7, where you would put the 7's, that's where you're putting the function itself back into itself. Here's another one of those expansions like I just did, so I'll go a little quicker this time, but if you aren't comfortable with using the trinomial square formula, just feel free to write that out side by side and do your FOIL. So this is going to go x squared times x squared would be x to the fourth. X squared times 4x would be 4x cubed, and then double it makes 8x cubed, and that'd be minus, so the minus. And then 4x times 4x would be plus 16x squared. And then we'll distribute minus 4x squared minus minus, make that a plus 16x. And then we just got to gather up our like terms. So we got x to the fourth right there. That's our only cube. 16 minus 4, so that would be 12. And plus 16x. This next one, same thing but a little bit harder because we have fractions. So to find f of g of x means we're going to evaluate f of x, so these x's are going to be replaced by g of x. So that would look like 3 over x over 3 over x minus 5. It's not considered simplified if you still have fractions within your fractions. So hopefully at some point you have seen complex fractions, which is what this is a fraction with fractions in it. And to do that, to clean this up, I'm going to use the common denominator, which in this case everything is over x except for this one. So x would be my common denominator for the three fractions. And I'm going to multiply by a clever form of 1 over here, which is x over x, that's still just 1. I'm putting the 1's down there to kind of show how the x is multiplying the numerators is what's going on. And what it's going to do is actually cancel a bunch of stuff. So here, if I thought of this as 3x over x, the x's would cancel and I would have 3. Here, if I go x over 1 times 3x again, this is the x's are going to cancel and I have 3. And here, minus 5 times x would be minus 5x. So that would be the simplified form of this. For g of f of x, that case we're going to put f into g. So it'll be 3 over x minus 5. In this case, the denominator for that 3 would be like a 1, 3 over 1 if I wanted to write that as a fraction. So the LCD for both of those is just the x minus 5. So that's what I'm going to use to clean this up. So I'm going to go x minus 5 over x minus 5. And again, I could write that over 1, but since that's just a whole number, I'm not bothering because in this case we had a fraction. So 3 times x would be 3x, and 3 times negative 5 would be minus 15. And then down here on the denominators, this would just cancel, and it would be over x. An alternative way to do this is to write it as 3. I couldn't do it here because I had two separate things in the denominator, two separate terms. But here I just have a number divided by a fraction. So I could write that as 3 divided by the fraction x minus 5, which is the same thing as 3 times x minus 5 over x. So I would do the reciprocal when we multiply fractions. And then distributing the 3 through, I would get 3x minus 15 over x. So two separate ways to simplify that one. They both work. With this one, that's really the best way to go. You could write this with a common denominator and then use this, but it would be a bit more work. So now we're asked to find the domain of a composite function. So when we're finding the domain of f of g of x, so we're defining g of x to be the inside function and f of x to be the outside function, we have to exclude any value that's not in the domain of g. So if plugging it into g would mess up g, then that's not going to be in the domain of our composite. And then this next sentence is a little tricky. We'll see it come up on one of the later problems. But find all values that are not in the domain of the outside function of f. And then I can't put things into g that make that excluded value of f. So for instance, let's say in the function f of x, let's say it's 1 over x, and x can't be 0. if that's my f of x. I can't put something into the inside function g that makes it come out 0, because then it will mess up the outside function. So I'll show that with some examples here. Given f of x is this, g of x is that, find each of the composites and then give the domain an interval notation. So this one's going to be reasonable enough that we don't have to, it'll simplify into some roots, and we'll be able to just kind of look at and see what the domain's going to do. For a later one, we're going to come back to this definition a little bit more. So let's see, let's find f of g of x. So f of g of x will be f evaluated at g. So that would look like 3x plus 2 plus 2. And let's look at minus, clean that up. So that would be 3x plus 4. So the domain of this one, remember for a root, the math under the root can't be negative. If it's negative, then we have an imaginary number, and that's not the domain. So this would be the composition of the two functions, and then to find the domain, we would say 3x plus 4 has to stay greater than or equal to 0. Bringing the 4 over, we have 3x has to be greater than or equal to negative 4. And then x, let me bring it up here, x has to be greater than or equal to negative 4/3. And in interval notation, greater than negative 4/3 would be bracket 4/3 and to infinity. For g of f of x, so for that one, this is going in for this x. So g of f of x would look like 3 times root x plus 2 and a plus 2 on the outside. So there's our function, and then x plus 2 has to be greater than or equal to 0, so x has to be greater than or equal to negative 2. So the ones involving a root are pretty easy because it's pretty clear with the root, since we can't have the square root of a negative number because it becomes imaginary, it's just the greater than or equal to 0, and that sets that up. So for this next one, we'll have a root again, but then we also have a fraction. And then remember, for fractions, like the domain for g of x, just as it is, would be x can be anything except for negative 24, because negative 24 would make this come out to 0, and we can't divide by 0. So those are two kind of big things that we run into in terms of domain, is fractions, denominators can't be 0, and for roots, the radicand, the math underneath the radical, that has to stay greater than or equal to 0. So this one asks us to find g of f and h of f, and then state the domains of each. Okay, so for g of f, there's g, there's f, so g of f would be 1 over 6x minus 18 plus 24. So this is going in for that x. So 1 over 6x plus 6. And then for the domain, we would say 6x plus 6, that's what can't equal 0. So 6x can't equal negative 6, and so x can't equal negative 1. So our domain, in interval notation, we have to, this is where interval notation is kind of a drag for this particular instance. It would be negative infinity up to negative 1, and then union negative 1 to infinity. So we're saying everything but 1. For the next one, it's supposed to find h of f. So h is this one, so 7 minus root, and then f is the 6x minus 18. And here, this time we have a radical, so we have to set that math underneath it, greater than or equal to 0. So it'll be 6x is greater than or equal to 18. X is greater than or equal to 3. And so from 3 to infinity, would be our domain for that one. Okay, so this is the one where we have to be a little bit careful. This one's a little tricky. This one's only asking us to find the domain. We don't have to find the composite of the functions. So you can see if I plug something into g of x and it messes that up with division by 0, that can't be in the composite. So for the g of x piece, we would say x minus 1 doesn't get to equal 0 because division by 0, so then x cannot equal 1. So that's the first number that doesn't work in our domain. For the f of x piece, by that same logic, right, x can't equal 4 because if it was 4, 4 minus 4 would be 0. So what we need to happen, or what we need to not happen, is we need where we plug a number in for this x, and then this thing comes out to 4, which then would be sitting right here in this x. And that may help a little bit when we see evaluating composites where we actually do that. But we need to not have g of x spit out a 4 because then 4 would mess up the denominator of f of x. So then we literally solve that. 4 equals 8 over x minus 1. Let's multiply both sides by x minus 1 to clear that fraction. So that would be 4x minus 4 equals 8. Bring the 4 over, 4x equals 12, and x equals 3. So that would be the other number that can't be in the domain. If you went to set up the composite of this and you simplified, it would come out, you would be able to see in the denominator that the x couldn't be 3. It's a bit of math, and it's a bunch of those kind of working with the complex fractions. So I think just finding the value and then setting g of x equal to it is probably the easiest way to solve that. In interval notation, so this is again a bit of a drag, negative infinity up to 1 union 1 to 3 union 3 to infinity. So that's the really long way of saying not 1 and not 3. That's what it would be an interval. And then lastly we have evaluating composite functions, and we'll look at that as a table and as a graph and then as functions itself. So f of g of 3, what that means is we evaluate g of 3 first. We start on the inside. So g of 3, and let's see, this is our input, this is our output for f and our output for g. So when x is 3, g is 7. And then that's going to replace g of 3, and we're finding f of 7. So when we plug in 7 into f, we get out 2. Same idea, the other notation, so f of 1 would be our inside function. And so evaluating at 1, f is 1. And then we're going to find g, the outside function, evaluated at 1. So when this is 1, g would be 3. G of 2 of 2, so that means we find g of 2 first and plug that result back in and get the final. So g of 2, there's 2, g is 5. And then finding g of 5, plugging into the outside function, 5, g of x happens to be 2. And f of 3, so when I plug a 3 into f, I actually get out a 3. And that's just going to loop eternally, because now I'm going to find f of 3 again, because we're plugging 3 into f, and it's just going to be 3 again. So here's the same idea, but reading instead of from a table, from a graph. So g of 2, and let's see, this graph is, there's f, and then that's g. So g of 2 equals 0, so then I have to find f of 0. Coming over here, that would be 4. F of 3, so when I plug, we'll do f of 3 first, plug 3 in, and we get out 2. And then that means we're going to evaluate f of 2 and plug 2 in, and we get out 5. g of 2. Okay, so g of 2 would be 0, and then we plug 0 into g again, and we get 2. And last one, g of f of 0, so f of 0 would be, f of 0 would be 2. Oh, I'm looking at g, my bad. F of 0 would be 4, and then g of 4 would be 5. So plug into the inside function, evaluate, take that answer, put it in the outside function, and evaluate. And then we'll see that same thing here, but just with some equations. So for this, I'm supposed to find f of g of 2, so my first step is to find g of 2, and that would be 4 times 2 minus 1, so g of 2 would be 8 minus 1, or 7, and then that is now g of 2 is 7, so we're finding f of 7. So that would be 7 squared minus, 3 times 7, or 49 minus 21, which would be 28. With that idea, coming back to this one for just a second. So here, like I was saying, x can't be 1 because that would be division by 0. The other thing we got was x can't be 3 because if I put 3 in there, I would get 3 minus 1 would be 2. 8 divided by, actually let me just go ahead and do it. So let's say we try to put 3 into g. So 8 over 3 minus 1, 8 over 2, and that would be 4. So if we're finding the composite of this, which isn't in the domain, so it shouldn't work, f of 4 now, when I go to plug that into the outside one, that's where that becomes undefined. So for the composite of that again, whatever messes up g of x, which in this case would be 1, can't be in the domain because it would mess up the first step of plugging in g of x, and then g of x can't spit out a 4 because that would mess up the second one. So hopefully that makes a little more sense with looking at how evaluating works. And then last one down here is g of f of 0. So we'd find f of 0 first, which would be square root of 4, so that would be 2. And then we're plugging that into the outside function. G of 2 equals 9 minus 2 squared, or 9 minus 4 makes